We have in earlier segments. So basically we have two methods, two probe method and four probe method. So in this case we have a four probe method developed by us. It is a four terminal arrangement for finding the temperature coefficient of resistance for copper. So we have a basic relation that sigma has electrical conductivity with n, that is the number of electrons or charge carriers, for consideration at the volume of, under consideration E, the magnitude of the charge, mu, mobility of charge carriers. So what is the point of interest in all the factors is mobility of charge carriers. Okay, mu. So mobility, which we can call as movement of carriers. So what is basically charge? Charge is movement of carriers. As the carriers flow, we can say the charge is flowing. So while focusing on this factor means it is basically a drift velocity that carriers attain or acquire by field, say electric field, which is applied per unit area. So we can say this flow or mobility, we can find it by charge carriers which are scattered by impurities or doping, defects in materials and vibration of the atoms. So suppose we increase the T temperature in pure materials, the dominance of scattering process is basically collision of charge carriers as they collide with the vibrating atoms. So as we raise further the value of temperature, we heat it further, the atoms will have more vibrations. But this vibration, this movement is not an ordered way. It is not in any particular fashion. So it is basically a vigorously movement, and by which it is not flowing in a vectored way. We can say the flow decreases, the movement decreases because of unlighted motion. So we can say the mobility decreases means flow decreases. In case of metals, the valence band is completely filled, so it has no business with the mobility or conductivity. The conduction band, which is point of interest here, is partially filled with the electrons. So means if there is some possibility of the movement here, it must be in the case of conduction band, not in the case of valence band. So the consideration in this case must be in conduction band because it is solely responsible for flow of charge, for flow of current. So the number of electrons per unit, like from this relation, coming to second point, n. So we have discussed mu, now n. It is temperature independent. So means the temperature, of course the other one is also the number of carriers. Number of carriers is again different material to material. So temperature variation of conductivity is basically studied through mobility of the carrier as the variation in temperature. So there are different approaches. In this case, the approach is discussed in this place. So I am just presenting the idea as I develop this theory, this experiment on these basic points. So we can say the mobility decreases as temperature increases. So the conductivity of matter, of course, falls as it is heated. We can say conductivity, which is the reverse of resistivity, specific resistance. So from this line, we can say the resistance of the material increases as you increase the temperature. characteristic of a metal. This is a metallic behavior. So again, focusing on TCR of copper, we call it as alpha. The resistance of length of copper wire at standard temperature, it is RT naught. We can call it as room temperature or specific temperature, reference temperature. And the resistance varies from RT naught to the particular heated temperature RT as you raise the temperature. So the relation follow this relation, means RT is equal to R resistance at reference temperature and plus this coefficient of resistance and how much temperature you have raised, how much it is heated. So mean temperature coefficient is just the manipulation from this is I have derived from first equation. Derivation from this equation shows that TCR of resistance is this value. So this first part I will deal with determination of alpha. So again I have some more for you to discuss. So let's start with this. This is the furnace old model. Of course it is not available now. I just want to show you in the further diagram. The newer ones that we are going to use below will be shown. So earlier, I think 3 years back, the furnace was of this type. It is a big container filled with wool, ceramic wool, and it's a tube in which you attach what you call insert, and it will be heated from all the ways. And this is the supply point where you can connect the DC power supply to heat it. So we need a DC regulated power supply, temperature controller, furnace, insert. The insert is almost same as I showed you yesterday. Only the upper segment is different because the inside the block which is not able to look at you holding the hand is only inside part. So I will just explain it and show you the upper segment of it. The lower one is block. I have the clips of upper section. You can see that. So insert that contains aluminium block as you see yesterday, which internally have of course PD 100. I told you it's basically coil of small platinum metal in which the variation is there. So 100 is at it shows 100 ohm resistance at 0. So a copper coil, apart from this, the other segment is copper coil that has 33 ohm resistance, and across the two ends we have current and potential leads. The current leads are exactly on the two ends because normally with the condition that current is measured when you connect a varying ammeter in series combination. And the normally it is like from the school education, ammeter is connected in series and voltmeter is connected in parallel. So similarly, we have a 4 probe setup. We can say 4 terminal arrangement. So current leads are connected at end and voltage leads are soldered at this point of the coil. So it's a 4 leads are there, 4 probe you can say like that. Constant current source, a DC voltmeter or a DMM which can find the value. The same, I think the picture I have taken from the manual. So what is here? A DC regulated power supply, temperature controller. Basically, temperature controller is a microcontroller based circuit. You just set the temperature, it will control the supply. You set it at 35 degrees, so it will cut the supply at 35 degrees. That is called temperature control. So here you have to set it at your own means. It will show you only the value of temperature basically. Okay. You have to regulate here because supply is at this end. So it is a DC electrical voltage which can be varied between 0 to 4 to 5 ampere depend on the load. And the voltage that you can vary is from 0 to 30 volt DC. So maximum power consumption is 60 watt and maximum current for this insert is 2 ampere. So temperature controller, the other one is furnace. Okay, furnace I show you old model, new model is better, compact and looks good. So insert is connected across the temperature controller, which contains platinum 100 resistor thermometer, which has a platinum resistance and show a 100 ohm resistance when it is at 0 degree. So at every 1 degree, the resistance vary 0.4 ohms. You can directly say for 10 degree change in the temperature, it shows 4 degree change in the 4 ohm change in the resistance. So it has a linear range of response from 170 degree to 400 degree centigrade. So per change in degrees 0.4 ohms. So we have a fine enamel coated wire. Enamel coated means it has basically 11 layers. One kind of insulation, transparent insulation. Like when we form an inductor or we have these fans in which we try to form a coil. When we run a fan, what happens basically, the current flows through it and it produces a field. So there are two fields, those are parallel each other. One is fixed field, other is moving field. The moving field provides just to the equipment. That's why it starts moving. So when we form a coil like this, so it must be insulated. It must be coated with some insulated material. That is, material here is enamel. So if it is not like that, it will be get short circuited. Suppose enamel moves from two conductive points, it will short it. So current always follows shortest path. It will not go to other part of the wire. So by this, the value of the field falls. So either it will short it or first it will short it and it will not able to produce the required field. So we have in this case is a 10 meter long wire which is wound on an insulating tube and fitted inside the hole on a rectangular aluminium block. So what is inside the block which is not directly shown, it is inside, it contains first a temperature sensor. Its leads are taken out at the top PCB which has separated terminals. I will show you the plate. So it is a 4-terminal arrangement which is used to find the resistance of copper wire. So two ends of the copper I just explained in just 2-3 minutes before. These two ends of copper wire are soldered to set at the edges a current leads, and two others are soldered to copper wire at 2 points. Those are just apart from those connected at the current points. So soldered current lead joints to find the voltage drop across the copper wire. So as you pass the current, of course it will drop some value. So that value must be noted down and we have a attachment of two separate wires and taken out. It is not like that we connect just very near, but very near to the edges. So we can find the drop across the whole length of the wire. So the other is aluminium block. We have a copper wire which is suspended within the furnace. Furnace is heated by passing the current through it using regulated power supply via temperature controller. So temperature controller comes in series, just for your knowledge. It is not in parallel. So voltage of the regulated supply is adjusted, means for per degree centigrade change, means that suppose it is at 30 degree, so within 1 minute it must shift to 31 degree. And the required voltage, this is just for your reference, the required voltage for the furnace for this change is 7.5 volt. Okay. So I think this is important for those who are going to do this first time. Every group will have the first time deal with the first setup. So those who are going to perform it first time, it will be helpful for them. Other way, take information from the senior batch. So two open ends of this ceramic tube, means ceramic tube I have shown here. So it's like this. So So two open ends are there to make a cooling more effective and reduce the convection losses to just plug with wool or with cotton. So voltage gradually increased as the temperature rises so that there should be a uniform heating rate. So temperature at 100 degrees C, it will be when it is at 100 degrees C, the voltage must be in between 8.5 to 9 volts. Mean around, you can say, for 60 to 70 degree, the variation in voltage is 1.5 to 2 volts. So post constant current, TCR is connected to current terminal of the coil. Coil is inside and we have taken out the individual leads. The current is set at 5 milliampere. Current is fixed because we use a constant current source. That's why it's a 4-probe arrangement. The current will remain stable throughout the experiment. So for that we use constant current source. So voltage is ready to increase the temperature. Basically, that I want to show from here. So voltage terminal of the copper coil are connected to DMN so that you can find how much voltage drop is here. So temperature of the furnace is shown on the temperature controller or temperature indicator. So for every 10 degree change in temperature, you just note down the reading. Suppose you start from 25 degree, you take first reading for 5 degree and then after 10 degree difference like 30, 40, 50 and so on. Okay. So how to set the current for the insert? So first of all, we have the display on this side. This is a range switch and this is a range switch, low and high. Very clearly show that what is the function of low and high. So when it is low, it a small resistance comes in picture, that drops the current. When you put it high, the switch is basically bypassing that resistance, providing the shortest path to the current. So current starts increasing. So basically that switch put in and put out a small value of resistance. That's all. So other is adjust the knob to leftmost position like this and connect the copper wire terminal to output terminal. Switch on the main and set the current. Current will be set from here in 5 milliampere range. So along with this, you will measure the voltage across the other terminals on that round PCB by using DM. So these are just standard set of readings which we have. So at that time room temperature was around 29-30 degrees. So it is started. Nowadays it will be less. It is around 20 to 22 degrees. So you just raise the temperature and find the value of voltage across the coil. So it will come in this picture. The other one, like this one, is this is measured value, this is calculated value. So we also find the difference between calculated value and measured value. So how it comes, I will show you on the next slide. Just have a look at that. How we find V calculated. V calculated is basically the intercept point multiplied by 1 plus TCR of copper and value of T here. So this is basically a practical value. So the difference is just written here and take its square. We call it as error. Means value of the measured minus value of the calculated. So how this comes? Just have a look at that. So this is a plot of voltage. This one is a plot of voltage and temperature. Plot of voltage on y-axis and temperature on x-axis. So just plot it at current 5 milliampere, which is fixed in the beginning. So we have a slope. We have software that will show you the slope, and we can find the intercept like this. Intercept V naught, either you just extrapolate it, it will show you the value. Suppose you start it from some of the value, it will show milliampere. So through the coil is this one. So you have a value of P, you have a value of current. Current is there, value of B is there, you can find the R. The other thing is, since we can say the resistance R, which is proportional to the voltage, as we vary the voltage. So the temperature coefficient alpha, which we can find from that equation. I just try to show that this equation alpha. Just need to find the alpha. What we have here, just see that we have alpha from this equation by simply replacing T naught by 0. Suppose it started at 0 degree. So we can say RT naught is that reference value by V naught, and we have this equation, and just substituting the value of the slope which we find from this plot, it comes out to be slope is alpha is slope by intercept. Slope is here, intercept is here. So just divide it, you will find TCR of copper. It is very easy. If you have some confusion, just have a look on the number. The things are given there. So standard value of alpha for pure copper is this. It is also available on the internet. Okay. So what calculated here is 4.64. So it may depend on matter to matter that is available inside the market. The purity content of the copper alpha. Okay. So I just brief it. So for metals, the electron in conduction band are responsible for electrical conduction of the metals. The temperature changes, means variation in the temperature, arises as the conductivity changes. Means you change the temperature, conductivity will change. And the mobility, means movement, decreases as you increase the temperature. So we can say the conductivity falls as the metals are heated. Okay. So temperature increases the resistance of the metal. So the formula used are here. So this is the contribution by my senior Manish sir. We just try to show it in a very easy way. So you have the standard equation like this. So what is the method? You know the value of current 5 milliampere. Although it is not, you just see that. Write it by current. What you get? Vt is equal to V naught alpha and T. So you just plot, you will get the value. This is again a very easy method. So I just want to have a look on the slide which we have discussed yesterday. It's the same slide from that discussion. So high resistance by leakage we have discussed. AC technique Professor Sundar has already discussed, I suppose. And this is 4-flow method, that is temperature coefficient of resistance. And 2-flow method is here. So I will discuss in the next part, that is energy gap of a silicon and find the resistance. So you have any query otherwise? So other thing is that this is a picture. So last वाले में आपको show नहीं हुई, you can see here. So actually setup दोनों का same है. As you run one, ठीक है? As you run one experiment, other one will be also along with that. So basically नीचे वाला segment है जो वो almost same ही है. कुछ है नहीं जो इन्होंने कल दिखाया था. सबने touch हो गया aluminium block and all. So it's almost like that. So it is shown here. During the discussion I will explain each and every one. So one thing more I just want to add, that when we calculate the band gap, we also have a very easy experiment in I think BSc and MSc lab. So we have that silicon wafer. Along with that, that is inside our institute. It may be available inside the institute. It is very easy method. So we have a silicon wafer on which we simply attach a thermometer, and we know that there is a heating coil. There is a heating coil. So heating coil heats that, and the temperature is shown on the thermometer. That is the cheapest way, not so accurate, but only for the purpose of undergraduate students, so they can understand what is happening here. In that case, along at the ends of that wafer, we have connected a, you can say, measuring device, DMS, that is showing the variation of drop or variation of flow of current. So basically, what students are doing, they just switch on the heating coil. So temperature increases, the electrons inside the wafer or inside the semiconductor receive heat, and the movement starts increasing. Although it is weakness there. So at some time, along with the increase of heat, they also note down the value of V on the DMS. So since it is a continuous heating, the vapor is heated and the value of voltage is noted down, which is shown on the DMS. So at some point, when there is a increase of V, along the full reading, they just note it. And plot it manually, they find the band gap. That is also a very easy method which I have shown. It may be before my joining, it's an old method. But in this case, it is very easy, very accurate, and you will get the accurate results by using this simple method. So band gap easily is calculated, is find out of a semiconductor. The semiconductor considered here is silicon. So the same relation I have, which we considered on the last discussion, sigma is NEU. So I just keep it. So what I want to say, the temperature dependence of electrical conductivity is, yes, reflects that the dependence of number of electrons and mu. So since in the last case we discussed mu and E, so we can say at room temperature in lightly doped semiconductors the mobility decreases because I already explained they receive a rigorous motion as we increase the temperature. So V is shown to be 3 by 2 from the literature. So band theory of the solid in small discussion, at 0 K the highest filled band is completely filled. Means what I want to say, balanced band is completely filled, and the next one, which is conduction band, is completely empty. So energy separation between top band and bottom of conduction band is called, yes, band gap or forbidden band. Why? Because there is no existence of the carrier across it. So we can say Fermi energy. What is Fermi level? Fermi level commonly says there is a highest probability of getting the carriers. So EF is middle of the band gap. So at finite temperatures, the electrons are excited to the bottom of upper band, means conduction band. So this is the only possibility which can contribute to conduction. So I just try to elaborate in convenient way via this diagram. So this is conduction band, this is valence band. So what and in between is forbidden band, okay, or energy band. So EG. So EG is a gap, or it is a gap inside the region of solids where no electron state can exist. So from this line, what want to say, as you increase the value of temperature, the discussion is on how these electrons from this point try to reach at the bottom of the conduction band. So there are various methods, like in the search, when people have a very beginning of their PhD, we have a method that is UV of the material, whether it is a powder, it is a slide, or it is a liquid material. So we have optical absorption, transmission, and reflection. So by all the way, it is just easy to calculate the band gap. So absorption, how much is absorbed, how much is allowed to transmit, and how much is reflected by changing the setup inside the machine. So of course, reflectance is more, we can say, advanced method, because setup has a, you can say, advanced technique, because it is the beam is reflecting back. So now other is two-probe method, contact resistance of leads and the random shape of the metals. The other one is, which we have earlier discussed, four-probe method, in which we have pressure contacts. Why I do that? That is the elimination of impedance of contribution of wiring and contacts. So it is shown here in a specific way, because it is very easy to design. Of course, you need some proper arrangement, but you just try to see that all the contacts are basically just like the pins of the watch. The pins of the watch also have two ends, and inside it is a small spring. So when you insert it inside, it comes out because of pressure inside the spring. The same mechanism is used here to make the contacts. It has spring loaded edge, which is always try to make a contact with the pressure. Basically, it is the pressure from the backside spring. So the circuit for measurement is shown here. That diode is here, which is considered as silicon. So it has 2 kilo ohm resistor and 470 kilo ohm resistor here, which is connected in series. Why it is connected? Because it will help us when it is forward biased. It will help us to control the value of the current, so that otherwise this diode can be damaged. And secondly, you can have a voltage drop here, so you can easily find the value of V. You can measure the value of V here. So PT100, it is shown here. It is the upper segment, upper side of the insert, which is shown like PT100 is connected here, and diode, this diode and this one are connected here. 2 kilo ohm resistor is connected here. So the value of the voltage drop will be find out from these two terminals. So and we provide a 9 volt fixed supply to find the values of V and I. So what is here? Let's discuss the basic theory. So in a diode which is made up of junction between P and N semiconductor, current will flow when a voltage is applied. For forward bias PN junction, what is the value of current? I is equal to I naught and exponential value of E, V, N, K and T minus 1. So you can see from this relation, it is easy to find out, not so easy, it is possible to find out K by P from this relation, which I have discussed yesterday. But since in this case, more variables are to be found out, more calculations need to be performed, so it may be little lengthy method and of course a little complex method. So that's why Sir has designed a separate using transistor only instead of diode, because Boltzmann constant K and electronic charge are also available here. But while you perform that experiment, you can also do that along with it, because other variables are available with you. You can just try to find out K by E also. So there is a factor, eta is called non-identity factor. It varies from diode to diode means when you purchase a diode, they also provide you data sheet. So from data sheet, you can note down the value of eta. It varies between 1.4 and 2. So at room temperature, the KT is around 0.025 electron volt. So even if V is small, means it is in the range of 0.3 volt, EV will lie between 7.5 and 11. So I can say this whole term means this whole term will be very less than, very greater than 1, means it will be more than unity. So neglecting this unity in comparison with this is justified. So now we have a plot of forward voltage which is shown on the DMM against log of I, which you calculate from here will get a straight line that has a slope alpha is equal to E divided by eta, K and T. Okay, so this is a very easy relation again to find K by E here. Okay, so knowing T, we can find the non-ideality factor for the diode by finding out the slope. So when we do the reverse bias, for reverse bias PN diode, we have this relation. It is clearly showing the negative value of the current. So I is called the reverse saturation current as it is independent of voltage applied. So it must be made of two individual contributions. The first one is diffusion current. Diffuser means carriers are diffused across the junction. They diffuse means they pass the junction due to difference in the concentration of electrons on the both P and N segment. So there is a difference of electrons means carriers, electrons and holes on P and N side at different ends of the junction. So we can say it's thermal excitation current because of creation of electron and holes by thermal energy. Means we are raising basically the temperature. So I naught will of course vary with the temperature and it will follow the relation A T 3 by 2 exponential minus of band gap and eta KT. So A is basically a standard constant which is commonly calculated when we discuss reverse bias segment. Take the log of this, log of this equation, you get this summarized value. So if we measure the reverse saturation current as we increase the temperature and have a plot means of these two terms against 1 by T, we will get a straight line and its slope beta is equal to minus Eg divided by eta K, Boltzmann constant. So knowing eta from the slope and log natural of forward current against voltage at room temperature and taking K to be like this, the energy gap can be easily calculated. So how to perform this? This is again which I have shown you earlier. This is the new furnace. Your first figure that furnace was earlier used. Now it is compact one. So we needed regulated DC power supply, temperature controller, furnace, multimeter, and insert that has same insert which we have earlier. Band gap to find band gap of silicon which contain a silicon diode. It is fixed with the help of iodide on the outer edge. You can see that the silicon diode. A 9-volt cell, of course, a same end terminal battery, 9-volt battery, and a setup for obtaining variable voltage from 9-volt battery. The same setup is here. So I'm just going to skip that. The same method is there, just inserted inside because both are same. So on the aluminum block of 1 cm square cross section, 5 cm length silicon diode with the number 1N4148 is pasted with arrangite. Okay, the two leads are insulated from one another and from the aluminum block by Teflon tray. PT100 is already fixed inside the block and it is clearly shown on the hole how PD100 leads are coming out. This block also contains copper wire, means there is the same setup which we had discussed just before this discussion. Coil of thin level coated copper wire having resistance 25 ohm. So we can find the TCR of copper and band gap of the silicon same time. Means it is the same setup, same furnace, only reading you have to note down on this page and this page. So electrical leads for PD100 resistance thermometer coming from the diode and for the copper coil are brought to a circular holder. So I just show you here, it is a circular holder. Leads are coming out from the inside aluminium block. So block is inserted into the furnace which is connected to regulated power supply through a relay. I just told in the beginning, it is not basically temperature controller, it is only temperature indicator. So it contains a relay which will either flip between to provide the supply or to cut off the supply. When the temperature is attained, the relay shifts to the other end, means cut off the supply. As the temperature falls, it again switch on the supply, so that temperature is maintained. So PT100 is connected to corresponding terminals which are shown on the circular PCB, and the voltage on regulated power supply is keep at 7.5 volt, which already shown during the beginning of the first discussion, so that the temperature of furnace raises 1 degree per minute, 1 to 1.5 degree centigrade per minute also. So two open ends of this ceramic tube are plugged together to prevent conventional losses. So means what I want to say, the procedure is same because you are doing the same thing repeatedly, and just note down the value on the other page. So means at 100 degree centigrade voltage will be 8.5 to 9 volt. So again I am showing the setup. You can see that PT100 is showing the both value. Diode is here along with 470k ohm, and the same I have shown you. So these are the just readings. This is a plot. You find the forward voltage here and voltage across 2.2 kilo ohm. Just take the log natural of volt and plot it again. So we get the eta ideality factor 1.87. Okay, which vary from diode to diode. K is here. So reverse saturation current as you raise the temperature, and it is just shown 30 degree in carbon. So 1 by Tk. So and also we note down the voltage across 470 kilo ohm, and we have a equation which I showed you earlier. Just have the value of this and plot it on this side. So this is on the y side and the 1 by T on X side. So you will get the band gap of this one. So again I just want to show that this is two probe method. One thing more, जैसे करने के लिए आपको बताया earlier it was basically a wrapper. The wrapper was earlier concealed inside the aluminium box, aluminium block. So 2015 we are going to sign an MOU with the academy. So, and so उस समय जब setup कर रहे थे, while doing the setup, wrapper was broken up. It was not showing the reading. It is about summer of 2015. Then sir recommended you need to purchase the wrapper from the local material company or either order it from some other vendor who is providing you the selling method. So that was not possible for such a short period of time because course is going to start exactly 1 day after. So the lab system is there, Mr. Jain from there. So we just have a very good option. He says that instead of connecting here the wrapper and purchase it, it is easy to connect the silicon directly because material is same, it is again silicon. So from that they made the modification permanently. So instead of connecting that diode, they connecting the wrapper, they connected say leave the physical material instead of value. That's all that is special. I think I already made that. You can ask the question. So these experiments are very easy. Only the temperature experiments take a little bit more because the temperature is rising, and especially it is recommended that there should be uniform heating. Uniform heating is there. So for uniform heating it takes a little long. But arrangement in the lab is such that there are some other experiments. Those are moving parallel to that, like small experiments, finding AY, finding high resistance using leakage method. So they also will have to do long parallel. So when you take the temperature, you note down the readings for 1 or 2 hours. Those experiments you can perform along with that. Thank you for patience listening. Thanks. This was very last discussion. Thanks.
ये आपका है